This is testing for a difference of two proportions. So again, using an example that we did when we did a confidence interval, scientists predict that global warming may have big effects on the polar regions within the next 100 years. One of the possible effects is that the northern ice cap may melt completely. Would this bother you a great deal, some, a little, or not at all? And so they asked this question to 680 people randomly selected from the American population. And then they asked it of 108 introductory statistics students at Duke University. And this is a summary of the answer they got. So, we want to test if there is a difference in the proportion of all Americans and the proportion of all Duke students who would say that they would be bothered a great deal by the polar ice caps completely melting. So, which of these is the correct set of hypotheses for testing if the proportion of all Duke students who'd be bothered a great deal by the melting of the northern ice caps differs from the proportion of all Americans who do? Both A and C are correct, right? Right? Because if you just subtract PUS from both sides, you get this. So you can either say that P Duke equals PUS, or you could say P Duke minus PUS equals 0. And same thing, but does not equal 0 because the question says differs and does not indicate the direction of the difference. So we're going to have a two-tailed test. And so we're going to use the not equal sign. The problem with B is that it's got the P hat. We know whether P hat is the same or not because we have that data. We're making inferences about the population. D is a one-tailed test, and the question doesn't indicate a one-tailed test because it doesn't indicate a direction. But you can write your hypotheses either way, A or C. Both of them will be correct. C is a little bit more intuitive because of the way that we calculate the test statistic, but either one is fine. Right? So when we're constructing a confidence interval for a proportion or doing a hypothesis test for a proportion, so if we're constructing a confidence interval, right, we used NP hat is at least 10 and N1 minus P hat is at least 10 for our large counts condition. When we're doing the hypothesis test for a population proportion, we checked NP0 and N1 minus P0, right? The expected number of successes and failures if the null is true. Which P do we use for two proportions? Both of them, right? Because our null hypothesis is that both proportions are the same. So in place of our P0, we use something called the pooled proportion, which is not nearly as complicated as it sounds. It's just the total number of successes from both samples divided by the sum of the totals from both samples. So for our Duke versus US example, there were 69 out of 105 Duke students who said they'd be bothered a great deal, and 54 out of 680 Americans. So our total was 523 people who said they would be bothered out of 785 total people sampled. So it's all the people who said yes out of all of the people who were sampled across both samples. And that ends up being a proportion of 0.666. So pooled proportion is just the total who said yes out of the total of all the people. So not really that hard. So, do these data suggest the proportion of all Duke students who would be bothered a great deal by the melting of the northern ice caps differs from the proportion of all Americans who do? So we're going to do a hypothesis test, right? So we state our parameter, which is the difference in the proportion of all Duke students and all Americans who would be bothered a great deal. So, difference in proportion of all Duke students and all Americans who would be bothered a great deal. Our statistic, P Duke minus P US, is 0.657 minus 0.668, which is negative 0.11. Our null hypothesis, we said, is that P Duke minus P US is 0, or that P Duke is equal to P US. I'm going to do this one. Again, you can do it. You could do that they're equal to each other if you prefer. It doesn't matter. And then our alternative is that P Duke minus P US does not equal 0. And our alpha equals 0.05. They didn't give us an alpha, but we're going to use alpha equals 0.05. Our plan step, we state the name of the test. This is a 2-sample z-test for a difference of proportions. So we could say P Duke minus P US, or P1 minus P2, or whatever. But it's a 2-sample z-test. And we check our conditions. Random. We're assuming that it's a random sample. The 10% condition, that 105 is less than 10% of all Duke students, and 680 is less than 10% of all Americans. And then we check our NP and N1 minus P. And remember, for that, we use the pooled proportion. So the pooled proportion, P pooled, was, which is technically P hat pooled, was 69 plus 454 over 105 plus 680. So the total who said a great deal out of the total. And that was 0.666. So we have to check that for each of our n's, though. So 0.666 times 105, which is something. Why is this not working? 0.666 times 105 is 70, which is at least 10. 0.334 times 105 is going to be then 35, which is at least 10. 0.666 times 680 is 453, which is at least 10, and 0.334 times 680 is 227, which is at least 10. Okay, so we checked our conditions. Now we calculate the test statistic, right? Our general formula is that the test statistic equals the statistic minus the null value over the standard error. So our statistic is PDuke minus PUS. All right, so that was negative was it 0.11 or it's 0.011? I was off by a decimal. My decimal should be there. Should be 0.011. So 0.011 is our statistic, and our null value is 0. So regardless of how you formulate the hypotheses, your specific formula is going to be P1 minus P2 hat minus, in this case, 0, because 0 is your null value for the difference, over the standard error calculation. You're going to, again, use the pooled proportion for the calculating the standard error, just like we use the pooled proportion. So P pool 1 minus P pool over N1 plus P pool 1 minus P pool over N2. So that is 0.666 times 0.334 over 105 plus 0.666 over times 0.334 over 680, and you take the square root of all of that. And you plug all that into your calculator and come up with a z-score of negative 0.22. And so if you draw your sketch of the curve, which you should always sketch the picture, you're going to get 0 in the middle. The difference is 0. We got negative 0.011, which is down here. But we also, because it's a two-tailed test, we have to check the positive 0.011 as well. So that's your z. Your p-value is going to be the probability that z is less than negative 0.22 or z is greater than positive 0.22, which is 2 times the normal CDF of negative 1e99, negative 0.22, 0, 1. And when you do that, if I thought I had, it gives you a p-value of 0.82. Right, you end up, when you do this, I thought I had the picture on here, but, right, it's 2 times 0.41, which is a p-value of 0.82. So, what do we conclude? Our p-value of 0.82 is greater than our alpha of 0.05. So, our conclusion, assuming that the null is true, that there's no difference in the proportions, there's a 0.82 probability of getting a PD minus PUS of negative 0.011 or lower, or positive 0.011 or greater purely by chance. And because 0.82 is greater than 0.05, we do not reject the null and do not have convincing evidence that a proportion of all Duke students who would be bothered a great deal by the melting ice caps is different from the proportion of all Americans who would. I'm not going to write the whole conclusion, but... Okay, so our population parameter is P1 minus P2. Our point estimate is P1 hat minus P2 hat. Conditions, random sample and 10% condition. They need to be, the two samples need to be independent of each other and randomly allocated treatments. And at least 10 successes and failures in each group using P pooled. Right, P hat pooled actually. And then your standard error, use P1 hat and P2 hat for calculating the standard error. For hypothesis tests, you use P pooled in calculating your standard error as well as in checking the large counts condition. And that's it for the difference of two proportions.